Alright, hello and welcome to this video on just an amalgamation of factoring techniques, or putting a lot of things together from previous videos I've made. You could call it a summary of factoring techniques, and what we're going to do here is just be simply looking at several examples where I'm asked to factor polynomials completely. So let's begin. Alright, the first of these, I'm going to start with my first examples are all going to have two terms, and then I'll slowly increase the number of terms to point out what you should be looking for. And it really does depend on the number of terms the polynomial has. Alright, so for all these I'm asked to factor the polynomial completely. Now, the first thing you should look for is the greatest common factor of all the terms. Now my polynomial here has two terms, 125y cubed and negative 64. These have a greatest common factor of 1. Alright, nothing else goes into both of these evenly. But that should be the first thing you look for, no matter how many terms the polynomial has. What's the greatest common factor? And if it's something other than 1, factor it out. Another thing to point out too is if the lead coefficient is a negative number, which is not the case here, but we'll see it coming up in future examples, pull out a negative, factor out a negative GCF, or the opposite of the GCF. Okay. Second, we're going to look at the number of terms. All right. How many terms does the polynomial have? Now this one has two terms. All right, like I said, that and that. Right? Now if it's got two terms, there's really only a couple, and you've already factored out the GCF. There's really only a few possibilities, a few situations where you're actually going to be able to factor the polynomial. So you can ask yourself, is it a difference of two squares? Alright, do you have the a squared minus b squared form? And if so, you can factor it to a plus b times a minus b, or a minus b times a plus b. If it's not a difference of two squares, is it a difference, let's put difference, is it a difference of two cubes? Does it have the form a cubed minus b cubed? So if it does, it could be factored to a minus b times a squared plus ab plus b squared. All right. And lastly, if it's not one of those forms, is it a sum of two cubes? So the form a cubed plus b cubed. Well, if it is, it can be factored to a plus b times a squared minus ab plus b squared. Again, I've made videos discussing all these different forms. Now, if the answer is no to all of these, if I see a polynomial with two terms and it's not in one of these three special forms, then I would just state that the thing is prime. If it's not in one of these special forms and you've already factored out the greatest common factor, chances are there's nothing you can do, right, to break it down any further, to factor it any further. Alright, so this one has two terms. I'm also noticing the minus sign here is a difference. And 125, 64, those are nice cubes. Whole numbers cubed, that's 5 to the third, that's 4 to the third, 4 times 4 times 4. And I'm also seeing a power that's a multiple of 3 on the variables in my expression. So cubes, I think it's a difference of two cubes. Well, let's see. let's break these down, these terms. 125y cubed, that is the same as 5y times 5y times 5y, 5y cubed. Minus, and I mentioned earlier, 64 is, 4 cubed. Right? So the 5y here is like the capital A in my difference of two cubes formula. The 4 is like the capital B. So everywhere there's an A in here, I replace it with 5y. Everywhere there's a B in here, I replace it with 4. And we can now factor this polynomial. The first one is just going to be A minus B, 5y minus 4, times, and then A squared. So that's 5y squared. 5y times 5y, or 25y squared, right? 5y times 5y. Then plus AB, 5y times 4. Well, 5y times 4 would be 20y. And then plus b squared, 4 squared is 16. And there you go. And in this sum of cubes, difference of cubes forms, when you have it factored, if you've already pulled out the GCF, or there is a GCF of 1, these should be prime. These shouldn't be able to be broken down any further when it's a degree 1 and degree 2. Right. Like this. So and you can double check, take this polynomial, take 25 times 16, that's 400. And can you think of any factors of 400 that add up to 20? I can't. Alright, so this is as far as it goes. 5y minus 4 times 25y squared plus 20y plus 16. And again, to double check, multiply. Distribute the 5y to these three, and then distribute the negative 4 to these three, and you'll see you get the 125y cubed, you get 100y squared, you get 80y, and then with the negative 4 you get minus 100y squared. That'll get rid of the positive 100y squared, that'll cancel. And then you get minus 80y, which will cancel you get rid of the positive 80y from earlier, and then minus 64. So you're left with those two terms up there. Fantastic. Okay, so I have another couple examples where we have two-term polynomials, and just basically if it's got two terms and I've already factored out the greatest common factor, is it in one of these three forms? That's the only way we're really going to be able to factor our polynomials with two terms. So here's another one. Two terms. Well, before I do anything, greatest common factor is 3. All right, if you look at these two, 24, 3 goes into 24 and 3 evenly. And since the lead is negative, since the lead is a negative number, I'm going to factor out negative 3 instead of 3, right? The opposite of the GCF. Now you could do that. I'm going to do this, or you could switch the order of the terms, put it as 3b cubed minus 24a cubed, and then go from there. So that way the lead isn't negative. But if you leave it this way, I'm going to factor out a negative. Okay, well, in doing so, negative 3 comes out. And if I remove a factor of negative 3, what's left over? Well, let's see, negative 3 times positive 8a cubed would be negative 24a cubed. And then negative 3 times negative 1b cubed would be positive 3b cubed. Okay, so I've factored it. Great, but is it factored completely? Right, so I got the factor of negative 3 pulled out. But now we look at this one in the parentheses. Is 8a cubed minus 1b cubed factored completely? Well, it's got two terms, right? It's got two terms, so we got to check. Ask ourselves: is it a difference of two squares? Well, my powers aren't multiples of 2, but it looks like it could be a difference of cubes, though. Right? My powers on the variables are multiples of 3, and it's a minus here. Let's see, I'll bring this over here. This is actually, you'll see, is a difference of cubes. Alright, 8a cubed is 2a times 2a times 2a, or 2a to the third. Minus, and then, I don't know why I'm doing the parentheses here, but b to the third is, b to the third. So it is a difference of 2 cubes. So this would factor then, as we saw in the previous example, we can factor a difference of 2 cubes. One is the, 2a minus b times, and then, 2a to the second, right? 2a times 2a, 4a squared, plus, and then 2a times b, so 2ab, and then plus, and then the b times b, b squared here at the end. Alright, so when we finish, right, when all is said and done, my original polynomial here, factor the negative 3 out, and then the next factor here in the parentheses factors even further, so we have negative 3 times, and then this factors to 2a minus b times 4a squared plus 2ab plus b squared. And that is that polynomial factored completely. And again, always check by multiplying. Multiply this factor and this factor, do all the distributing and combining like terms, you'll get this back. And then multiply by negative 3, you get this back. Wonderful. Okay, another one with 2 terms. I've got several. Here I have x to the 4th and plus negative 1 or minus 1. So the GCF, first thing you always look for is just 1 here, right? Look at both terms. Nothing goes into both of those evenly, so just the number 1. So nothing to factor out of all the terms. And it's got 2 terms. And look at my powers here. The powers on the variables this time is a multiple of 2, not a multiple of 3. So I'm thinking this is probably a difference of 2 squares. Right? So let's see if that's true. Like what to the second power, what squared would give me x to the 4th? Well, that'd be x squared, right? X squared times x squared would be x to the 4th. Minus, and then 1 to any power is 1. So 1 squared is 1. So this is a square minus a square. This is a difference of 2 squares. Okay, and remember how that factors. Again, go back to the previous page. A squared minus b squared factors to a minus b times a plus b, or a plus b times a minus b. So the a here is this x squared, and the b is the 1. So the way this would factor would be x squared plus 1 multiplied by x squared minus 1. Okay. So I have factored the polynomial, right? It is now factored, and you can check by multiplying. Multiply these two, you get x to the 4th minus 1 back. Great. But is it factored completely? So let's look at this first one here. Now this first one, it's got 2 terms, but this one is a sum of 2 squares, x squared plus 1 squared, or 1. So that's prime, right? You cannot, if you've already pulled out the GCF, a sum of 2 squares is prime when you say, well, it can't be factored over the integers, they would say for this one. However, this factor, see I have a difference. This is x squared minus 1 squared. This is a difference of 2 squares again. So this second factor I've written here can be factored further, right? This is x squared minus 1 squared. So that can be factored further to x plus 1 times x minus 1, or x minus 1 times x plus 1, whatever you prefer. So when all is said and done, when I'm factoring x to the 4th minus 1, it factors to x squared plus 1, which can't be broken down any further, that's prime, times, and then x squared minus 1 can be broken down further, so times x plus 1 times x minus 1. And there you have it. Right? These factors can't be broken down any further over the integers. And double check, multiply. When I multiply these two, I get this. And then when I multiply these two, I do get the original back Great. All right. So I have another example here where we have a polynomial with two terms. Negative 36x squared y plus 16y. All right, so this time, again, as with every time, I look for the greatest common factor first. Now, they both have a y in it, right? So the greatest common factor will have a y to the first. And 4, right? This is 4 times 9, or negative 9, right? But the 4 goes into 36, and this is 4 times 4. And that's the largest number that goes into those coefficients. So the greatest common factor is 4y, and since the way I have it written here, if you want to switch the order of the terms, that's fine, but the way I have it written, I'm going to leave it this way. The lead is negative, so I'm going to first factor out the opposite of the GCF. Okay, I'm going to factor out negative 4y. Okay, if I do that, let me see, we pull out, here's negative 4y coming out. And if I remove negative 4y, what's left over? Well, negative 4y times positive 9x squared would be left over. That would make my negative 36x squared y. And then negative 4y times negative 4 would be positive 16y. Alright, so it's factored now. But again, is it factored completely? Well, if you look at this, where there's a GCF, you're not going to break the GCF down. It's just simply its own thing. 9x squared minus 4. Two terms, got a square there, a difference. I'm thinking this is a difference of two squares. Alright, now let's write diff of squares. Well, let's see. 9x squared, that's the same thing as 3x to the second, right? 3x times 3x is 9x squared. Minus in 4 is 2 squared, right? 2 times 2. So yes, it is a difference of nice squares. So the way this factors would be 3x plus 2 times 3x minus 2. And then we're basically done. Let me just write the end over here. Right, so I factored out the opposite of the GCF. I took this and we pull out a negative 4y. So I have negative 4y times, and then this 9x squared minus 4 factors to 3x plus 2 times 3x minus 2, or 3x minus 2 times 3x plus 2, whichever your preference is. And there you go. There's our original polynomial factored completely. And again, double check. If I multiply these two, I would get that one back, and then multiply these two, I would get that one back. It'll work out. Wonderful. Alright, so I have one last example of two-term polynomials. 6xy squared, and then a positive 15x cubed, right? Plus 15x cubed. So again, first thing, always, what's the greatest common factor of all the terms? Well, I'm noticing they all have at least x to the first, right? So you're going to have x to the first in your greatest common factor. And if you look at the coefficients, 6 and 15, the largest number that goes into both of those is 3. Alright, so 3x is the greatest common factor of these two terms. Alright, so if I remove 3x, so the factor of 3x comes out. When I remove the factor of 3x, what's left over? Well, if I pull out 3x, what's left over in the first one would be 2y squared, and then plus, and then 3x times 5x squared would be 15x cubed. Okay, so I've factored the GCF out, and then this next factor, yeah, it's got two terms, right? 2y squared and 5x squared. It's not a difference though. And you got squares. You can't factor a sum of squares over the integers. And 2 and 5 aren't nice squares, right? What the square root of 2 is like 1.4 something, right? And the square root of 5 would be 2 point something. Not nice. So that's as factored as that's going to get. All right? A sum of squares where the coefficients aren't nice perfect squares. Can't break that down any further, unfortunately. So this would be it. Just what I got when I pulled out the greatest common factor. Just 3x times 2y squared plus 5x squared. And that's it. That is this thing factored completely. And again, double check by multiplying. Distribute the 3x. You'd get your 6xy squared plus 15x cubed back. Okay. So always GCF first. And then if it's got two terms, if something's got two terms, is it a difference of squares, a difference of cubes, or a sum of cubes? And that's really all you can handle right now. Alright, so what if it has three terms? Okay. So again, always first GCF. Alright, factor out the greatest common factor or the opposite of the greatest common factor if the lead is negative, which is not the case here. And then second, you look at the number of terms. I know I've written this already, but here it is again. You look at the number of terms. Now what if it's got three terms, which this has? Okay. 2p squared, positive 8p, and negative 90. If it's got three terms, you ask yourself this question: is it in this form of a quadratic where you have a times something squared? X represents just anything. It doesn't, here it's p's, right? A times something squared plus b times that same variable, and then plus c, where a, b, and c are numbers. Is it in that form? Or is it one of those perfect square trinomials? Is it in this special form? I remember this from the previous video, where we have a squared plus 2ab plus b squared, right, where a and b, these capital A and B, can represent any expression. If that's the case, you can factor that as a plus b times a plus b again, right, or a plus b squared. Or is it in the form a squared minus 2ab plus b squared? If that's the case, then you can factor it to a minus b times a minus b, or the quantity a minus b squared. And remember, there was a procedure for factoring things of this form up here, where I took a times c, you took a times c, and then tried to find factors of that product that added up to b, and then you could factor by grouping, or guessing and checking, or whatever, trial and error. We'll see an example of that as we go along. All right. So the first thing we do, right, is find the greatest common factor. Now, if you look at these terms, 2p squared, 8p, and negative 90, right, the greatest common factor is 2. All right, that goes into all the coefficients evenly, and that's it. So I pull that out first, and then you got p squared, and then 2 times 4p, right, plus 4p, and then 2 times negative 45 would be negative 90. Right? So I have 2 times p squared plus 4p minus 45. Pull the GCF out. So great, it's factored, but is it factored completely? Right? Well, no. We have to look at this now. Right? The GCF, leave that on its own, great. But this p squared plus 4p minus 45, that's in this first form here. Right? It's where x is p, right? The x's are p's, and a is 1, little b is 4, and little c is negative 45. So remember how I worked that out. You take a times c, which in this case is 1 times negative 45. That's negative 45. And then you tried to find a pair of factors of negative 45 whose sum was b, or this positive 4. Now those factors, you can play around with it. Right? One's got to be positive, one's got to be negative. I want the sum to be positive, so that means I want the positive number to have the larger magnitude, the larger absolute value. So it could be negative 1 and 45, or, and then the next one that I'm going to say is correct, negative 5 and positive 9. All right, those multiply to be negative 45, and they add up to be positive 4. And then you could try the grouping. All right, now because the a is 1, right? This is 1p squared. I know that the factors of this are going to be p minus 5 and p plus 9. Remember that little shortcut? But you could also do the grouping thing where I take the negative 5 and 9, this pair of factors I found, rewrite the middle term. So instead of positive 4p, I rewrite minus 5p and then plus 9p. Right, that's the same thing as positive 4p, and then minus 45. And then we do factoring by grouping, where I put first two terms in a group plus second two terms in a group. Then we factor each half, factor each group. First group has a common factor of p, right? So p comes out, and then you have p minus 5 left over, plus, and then the next group, greatest common factor of this group, this half, is 9. I pull a 9 out. Then you'd have p minus 5 left over, and then you see p minus 5 is a common factor of both these products, so p minus 5 comes out, and what's left over is p plus 9, right? So as I mentioned, if you find this pair of factors in this procedure and the lead coefficient is 1, you can just say, the variable plus one of these numbers times the variable plus the other one, p plus negative 5 or p minus 5 times p plus 9. All right. But if the lead coefficient is not 1, then I'd actually go through this grouping procedure. All right, so finally, when this is all said and done, 2p squared plus 8p minus 90 would factor completely to 2, right, the GCF pulled out, times, and then the p minus 5 times p plus 9. And there you go. And you can double check again by multiplying, right? Take p minus 5 times p plus 9. You get this, and then if you were to multiply by 2, you'd get the original expression back. All right, so there's another one with 3 terms. And going through the same steps. Now, one other thing I'll point out is that if we don't have something in one of these forms, if it's got 3 terms and it's not in one of these forms, then we can't really handle it right now. All right. There are other factoring methods, but these most recent videos I've been putting up are for, like the basic methods, the introductory factoring methods. So if a 3-term polynomial isn't in one of these forms, either it's going to be prime or there's just some other way to factor it that we haven't seen yet, or we aren't equipped to handle just yet. All right. So be aware of that. So these 3 terms here. Negative 45x cubed, positive 3x squared, positive 6x. The greatest common factor would be 3x, right? They all have at least x to the first, and 3 goes into all the coefficients. And because the lead is negative, I'm going to factor out the opposite of that, right? I'm going to factor out negative 3x. All right, so let's do that. So here's negative 3x coming out. And when I remove this, what's left over in here would be what? 15x squared minus x. Right? Negative 3x times negative x would be positive 3x squared. And then minus 2. Okay. Got the GCF out, or the opposite of the GCF out. Great. And then we look at this. And again, this is in that form, the ax squared plus bx plus c, where a is 15, b is negative 1, c is negative 2. So I'm going to take a times c, right? 15 times negative 2 is negative 30. And then what I'm looking for is a pair of factors of negative 30, 2 numbers that multiply to be negative 30, but they add up, have a sum of negative 1. And that'd be negative 6 and positive 5, I hope you can see. Right? Negative 6 times positive 5 is negative 30. Negative 6 plus 5 is negative 1. All right, and then here comes, I'll bring this over here. Here comes the grouping part. I'm going to rewrite this. This is 15x squared. And then I'm going to rewrite the middle term using these numbers, right? Minus 6x and then plus 5x. And we're going to do the grouping now. The first 2 terms in a group, big plus sign. Second 2 terms in a group, I got 5x minus 2 at the end there. All right, there's still a minus 2. And then I factor the first group. These have a common factor of 3x, right? So 3x comes out. and then what's left over would be 5x minus 2. And then the second group, 5x minus 2, the greatest common factor of this group is just the number 1. So if you'd like, you can always pull out a 1. That doesn't change anything. So if you want, you can write the number 1, pull out a 1, and then times 5x minus 2. And then both these groups have 5x minus 2 as a common factor, so 5x minus 2 comes out. And when 5x minus 2 comes out, you're left with 3x plus 1. And if you were to multiply these two together, do the FOIL and combine like terms, you would get 15x squared minus x minus 2. Alright, so when all said and done again, our original polynomial, this guy here, pull out the negative 3x, right? So negative 3x is still a factor, times, and then this other polynomial, 15x squared minus x minus 2, factors to 5x minus 2 times 3x plus 1. And there you have it, right? This is the original polynomial factored completely. And double check, multiply. When I multiply these two, I get this, and when I multiply these two, I get that. Right? And you can double check that on your own. Alright, so here's yet another example of a polynomial with 3 terms. It's going to be a bit of a longer video today. Alright, so I look at the GCF. Now here, the greatest common factor of all 3 of these terms is 1. So nothing to pull out. And then, it's in that form, ax squared plus bx plus c, where a is 8, b is 22, c is 5. Alright, so I take the usual steps. A times c, 8 times 5 is 40. And then I'm looking for a pair of factors of 40 that have a sum of 22, and that would be 2 and 20. Alright, 2 times 20 is 40, 2 plus 20 is 22. Alright, and then we'll go to the grouping. So in the first group, I got the first 2 terms would be 8x squared, and I'm going to rewrite 22x as positive 2x plus 20x, right? A positive 2x and a positive 20x. So I'll put the positive 2x in the first group, then I got a big plus sign, and then in the second group, the positive 20x, right? So there's your 22x. And then you got the last term plus 5 in that second group. I factor the first half. These have a greatest common factor of 2x, right? 2x comes out. If I pull out a 2x, what's left over will be 4x plus 1, right? Don't forget when you remove something completely, there's still 1 left over, right? 2x times 1 would be 2x. Plus sign, and then the next group, when I factor the next group, the greatest common factor is 5. Pull out a 5 from that, and what's left over would be, again, 4x plus 1. And you're seeing the factor of 4x plus 1 in each of these products. I pull that out. Pull out the greatest common factor of 4x plus 1 from these two. And when 4x plus 1 is removed, the other factor is 2x plus 5. And there you go. Alright, 4x, so 4x plus 1 times 2x plus 5 would be 8x squared plus 22x plus 5. And again, double check by foiling, distributing, multiplying. Distribute the 4x, distribute the 1, combine like terms, you will get 8x squared plus 22x plus 5 back. Okay, here's yet another example of a polynomial with 3 terms. Alright, so I look at all 3 terms. What's the greatest common factor? Well, they don't all have the same variables, so there's no variables in the greatest common factor. This is 12 is 2 times 2 times 3. This is 2 times 2 times 2 times 2. And this is 5 times 7, or negative 5 times 7. So these have some 2's. 4 goes into these, but not into that one. There's no common factor other than 1. So the greatest common factor is, again, just 1. Meaning, I just, if it's in that form, which it is, ax squared, well, am squared plus bm plus c is one of those quadratic trinomials where a is 12, b is negative 16, c is negative 35. I'm going to go through that same procedure. A times c, that's 12 times, negative 35. Okay, let's see. That'd be negative 420, right? Because this is negative 5 times 7, right? Negative 5 times 12 is negative 60. Negative 60 times 7 would be negative 420, right? All right, so negative 420, and then I'm looking for a pair of factors, and you might want to do guessing and checking or trial and error here. I'm looking for a pair of factors that multiply to be negative 420 and add up to be negative 16. All right, so maybe I'll actually make a little chart here because I'm not seeing it immediately. Factors of negative 420 and their sum. And I want their, so if they multiply to be negative 420, that means one has to be negative, one has to be positive, and I want them to add up to be negative. So the negative one has to have a larger magnitude, has to be have a larger absolute value. Okay, so I mean, an obvious one would be negative 42, and I mean you could start off with like negative 420 and 1 and all that. I'm just going to mess around. I'm not going to go in any particular order. I'm just playing around with factors. Obviously negative 42 and 10, but those add up to negative 32, right? Not negative 16. Now I'm seeing some up here, right? You got negative 35 and 12, but those, when you add them together, make negative 23. Now we're closer to negative 16, so that's good, but still not the correct pair of factors. Let's see, maybe let's see, this is 2 times 6 is 12, and 5 times 7 is 35, and about 4. Here we go. 2 and 7, 6 and 5. 2 and 7, 6 and 5. 2 and 7 is 14. 6 times 5 is 30. And make the 30 negative. One has to be negative, one has to be positive. And look at this, right? Negative 30, positive 14. That's negative 16. That's what I want. Okay. So again, that was. That's not hard. That's not easy to do when the numbers are larger. I'd say this, maybe go in order. Start at 1 and work your way up until you get to 14, goes into 420, and then you'll see it. Maybe that might take a while, but it's still doable. Yeah, unfortunately, that's the way you'd have to go about it. Or you could do trial and error. I've put up a video before about factoring these things by trial and error. Anyway, back to this, the grouping part. So in one group, we got 12m squared, and then I'll put the plus 14m, big plus sign, and then the next group, negative 30m. All right, positive 14m in one, negative 30m in the other group. That make my negative 16m. And then you got minus 35. All right, you factor the first half. These have 2m as a common factor. I remove 2m. And then that would be multiplied by 6m plus 7 plus, and then this next group, the greatest common factor is 5, but because the lead is negative, I'm going to pull out negative 5. All right, the lead is negative in there, and when I remove negative 5, you have 6m plus 7 again, and hopefully you're seeing now the 6m plus 7 in common. I remove 6m plus 7 times, and then what's left over when I remove 6m plus 7 is 2m plus negative 5, or just 2m minus 5, right? And there you go. 6m plus 7 times 2m minus 5, and go ahead and FOIL and combine like terms. You're going to get the original back. All right, so here's yet another one. Now we haven't seen yet an example where I've said, hey, that looks like a perfect square trinomial. All right. Well, so here's one. Right? It's got 3 terms. The greatest common factor of all 3 terms is 1. Right? They don't all share anything other than the factor of 1. But look at what I'm seeing here. See how the first term is a nice square, p squared, and the last term is also a nice square. 36q squared is 6q squared. So I've got p squared, and the last term is plus 6q squared. So I'm thinking, hey, maybe this is a perfect square trinomial. where you have something squared, and then, this would be the minus one here, minus 2 times that thing times the other thing, 2 times ab plus b squared. And this can factor to a minus b times a minus b, right? I've written this up before in this video, where a is p and the b is 6q. All right. So is the middle term 2 times p times 6q? 2 times p times 6q. Is that the middle term? Yes. So this is, in this form, it is a perfect square trinomial, meaning I can jump to the end. I don't need to do any grouping. I recognize this, the perfect square trinomial. This will factor to a minus b times a minus b, where a is p and b is 6q. So p minus 6q times, itself. So it's p, and check that out. Take p minus 6q times p minus 6q, FOIL and combined like terms, you'll get p squared minus 12pq plus 36q squared back. So I'm done. That's that polynomial factor completely. Now you could also have done it the a times c way, where I'm noticing it's quadratic. It's in a nice quadratic form in both p and q. It's very symmetrical. Everything is a degree 2 term. I take 1 times 36, the lead times last, a times c. And then factors of 36 that add up to negative 12 are negative 6 and negative 6. And if you're finding that those factors are the same two numbers, negative 6 and negative 6, then you have a perfect square trinomial. All right, so that's another way to recognize that. All right. So another example where I have 3 terms. 75x squared plus 90x plus 27. Now this time, the greatest common factor is 3, right? 3, this is 3 times 25, this is 3 times 30, this is 3 times 9. So I pull out 3, and what's left over is 25x squared plus 30x plus 9. But, so I factored it, but again, I'm trying to factor completely, right? So we got to look at this guy now in the parentheses. Can I factor that any further? Well, like the example before this, look at, there's 3 terms. Look at the first term. It's a nice perfect square, right? 25x squared, bring this over here, is the same thing as 5x squared, right? 5x times 5x. That's a nice square. The last term, 9, is a nice square, 3 squared. So the first term in here is a nice square. The last term in here is a nice square. Is that middle term, so I have the a squared, I have the b squared, is that middle term plus 2ab? Because if it is, then we have a perfect square trinomial, and it'll factor to just a plus b times a plus b. So is the middle term 2 times 5x times 3? Well, that would be 30x, and yes it is. Yes it is. So indeed I have a perfect square trinomial, and that means that this factors to just, a plus b squared, or 5x plus 3, that quantity squared, 5x plus 3 times 5x plus 3. So when I'm all said and done here, I factored out the 3, right? So 3 is a factor, times, and then this guy here in the parentheses factors to 5x plus 3 times 5x plus 3, or the quantity 5x plus 3 to the second power, and there you have it. And again, double check by multiplying. Square this, you'll get this. Multiply by 3, you get that. You get the original back. All right. Okay, and then I've got one more example where you have 3 terms, and then we'll get into just a couple where you have 4. All right. So polynomial with 3 terms again. Greatest common factor of all 3 terms is again 3, right? 3 goes into 3, 9, and 21. But the lead coefficient is negative the way I have it written. So what I'm going to do is factor out negative 3. Okay, let's do that. So I pull negative 3 out. And if I remove a factor of negative 3 from all these, what's left over is z squared. And then minus 3z. Right, that'd be positive 9z. And then plus 7. Right, negative 3 times positive 7 would be negative 21. Alright, so I've factored out the GCF. Now we're looking at this again. So this is not, the first one's a square, but the last term is not a nice square, right? 7 is not a nice square. The square root of 7 isn't a whole number. So it's not going to be a perfect square trinomial. So I'm going to do that a times c thing, which is 1 times 7, right? 1z squared plus 7. That's 7. And then can you find any factors of 7 that add up to -3? Well, if they're factors of -7, that means, of +7, sorry, +7, means they both have to be positive or both negative. And I want them to add up to -3, so they both need to be negative to have a negative sum. Let's see, the only factors of 7 are 1 and 7, so the only possibility here would be -1, -7, but that does not work, right? Those add up to -8. Right? Their sum's -8, and that's the only possibility. That's it. So that tells me that z squared minus 3z plus 7 is prime. Right? So this guy in the parentheses is prime. So that factoring out of -3, that is the only factoring I can do in this particular problem. So I pull out -3 times, and then again it's z squared minus 3z plus 7, and then that would be it. That would be this polynomial factored over the integers completely. I'm done. Alright, now I've got just 2 more examples. Again, sorry about the length of this, but we've seen problems where there's 2 terms. We've seen polynomials with 3 terms, and how to approach them if they're in specific forms, right? And again, this is very basic factoring techniques, where things need to be in a particular form for us to be able to factor them. Now what about, what if there's 4 terms? Okay, so again, said this multiple times now. First, greatest common factor. Look at all the terms, all 4 of them is their greatest common factor. Or if the lead is negative, pull out the opposite of the greatest common factor. Then look at the number of terms. Now I've talked about what if there's 2 terms, what if there's 3 terms. If there are 4 terms, we're going to try factoring by grouping. All right, and I'm going to say try factoring by grouping. And you've seen me group already in this video, where I'm going to break it into 2 groups and then factor each group and then factor what remains. If that doesn't work out, then you're going to have to go through. You're going to have to learn some other techniques. There's other factoring techniques that you will see in later in a college algebra course, where you use something called the rational zeros theorem and the factor theorem to help factor polynomials of degree 3 or higher. Right? This is a degree 3 polynomial because the highest power in x is 3 here. But for right now, we're again just going over the basic techniques. So if this doesn't work for me, if grouping doesn't work for me here, I'm going to say inconclusive. I don't know if it's prime or not, but I'm going to guess it's prime, but to say it's inconclusive, I don't know what to do. I can't go any further with it until I learn some more advanced techniques. Okay, so here I have 2x cubed plus 3x squared plus 4x plus 6. The greatest common factor of all these terms, look at all 4 of them, is 1. All right, that's the only thing that goes into all of them evenly. So I don't pull anything out. So here comes the grouping part. First 2 terms in a group. Big plus sign, and then second 2 terms, positive 4x, positive 6, in another group. Then I factor each group. All right, the first group has x squared as a common factor. All right, they both have at least x squared, and when I remove x squared, we have 2x plus 3 left over. Then plus, and then look at the second group. These have a common factor of 2. Right? 2 goes into both 4 and 6, so I pull a 2 out, and then what's left over is 2x plus 3. And then look, if these 2 factors that are remaining are the same, right? Notice how they're both 2x plus 3, then it's factorable by grouping. You're doing all right. If they're not the same, you might want to rearrange the terms, maybe switch a couple terms and try it again. But if it still doesn't work out, then you gotta say inconclusive here. I don't know if I can factor this. I might need to learn some more advanced techniques. But right now this is good. Right? Both of these products have 2x plus 3 as a common factor. So I remove that, right? That's like the GCF of this whole expression here. Pull out 2x plus 3, and when I remove the factor of 2x plus 3, what's left over is x squared plus 2. And then we look, 2x plus 3 is as factored as that gets. That's a degree 1. Here I have a quadratic, a degree 2. Now if this was like x squared minus 4, or x squared minus 16, or some difference of squares, right, I could factor it further. But it is a sum, right? X squared plus 2, and 2 isn't a nice square anyway. So this is prime. I cannot factor this down any further. I am finished. Alright, so 2x cubed plus 3x squared plus 4x plus 6 factors to 2x plus 3 times x squared plus 2. And again, double check by multiplying. Distribute the 2x, distribute the 3, combine like terms if there are any, and you're going to get those 4 terms back. You're going to get the original back. Alright, so finally, my last example, another polynomial with 4 terms, another degree 3 polynomial here. You got 6x cubed plus 9x squared minus 6x minus 9. Again, greatest common factor first. Now this time, 3 does go into all of these. Alright, 6, 9, and 6 and 9. And the lead coefficient's positive, so I'm just going to pull out 3. Alright, so I'm going to pull out the 3. And once I remove the 3 in the next factor, I write, what's left over. And it'll be 3 times, 2x cubed plus 3x squared minus 2x minus 3, right? And if you were to distribute the 3, right, that would give you that back. And then, I factored it great, but have I factored it completely? I still have to look at this factor in the parentheses and see if that can factor any further. Alright, so I bring this over here. It's got 4 terms. So I'm going to try the grouping where I cut it in half and all that. Say 2x cubed plus 3x squared. Put those first 2 terms in a group. Again, I prefer to put a big plus sign to separate my groups plus. And then the next 2 terms in a group, the negative 2x and the negative 3. Alright, so from the first group, I can pull out x squared, right? These have a common factor of x squared. And then you have 2x plus 3 left over. Plus, and then from this second group, the greatest common factor is 1. I'll put that here. The greatest common factor is 1, but the lead is negative, right? In this group, the lead is a negative number. So what I'm going to do is pull out negative 1. So you see my negative 1 come out. Now if I remove negative 1, negative 1 times 2x would be negative 2x, and negative 1 times positive 3 would be negative 3. So again, I get the 2x plus 3 showing up. Great, the same factor in both of these products. So this has the greatest common factor now of 2x plus 3. And if I remove that, what's left over is what? X squared plus negative 1. So x squared plus, now plus negative 1 is just minus 1. Okay. So back here, we removed a 3. Alright, so that's a factor. 3 came out. Times, and then the way this factors is 2x plus 3 times x squared minus 1. Okay, now I've factored it further. But can it be factored any further than this, right? Through GCF we're going to leave alone. 2x plus 3 is a linear, a degree 1. That's as far as that goes. But the degree 2s are higher. We can see if those can factor any further. Well, look at this. X squared minus 1. This is a 2-term polynomial, and it's a difference of squares. Do you see that? X squared minus, and then this would be 1 squared. What I have here is a difference of squares. And if you remember from earlier how this would factor, x squared minus 1 squared would factor to x plus 1 times x minus 1, or x minus 1 times x plus 1. So when all said and done, finally, we have the 3 that we pulled out earlier, times, and then the 2x plus 3 was one of the factors of the next thing, right? This guy here, times, and then x squared minus 1, difference of squares, that can break down even further to x plus 1 times x minus 1, and now all these are degree 1 or lower. This is as far as I can go. That is factored completely. And double check. If I multiply these two, I get this. And then if I multiply these two, I get this. And then multiply by 3, I get that. You do have an expression down here that is equivalent to the original polynomial we were given. Great. Okay, so I know it's a lot. It really is just an amalgamation, a collection of all the techniques we talked about and I've made in previous videos. But just telling you what to try to look out for, what to recognize. So again, first thing, greatest common factor, or the opposite of the greatest common factor. Pull that out if the lead coefficient is negative. Then how many terms does it have? If it has 2 terms, you'll be able to factor it if it is a difference of squares, a difference of cubes, or a sum of cubes. And that's really it right now. Does it have 3 terms? If it does, is it in that ax squared plus bx plus c form where you can factor by grouping or trial and error, or is it a perfect square trinomial? And then if it's got 4 terms or more, if it had something with 5 terms, you might try grouping 3 terms here, 2 terms there, or something like that. But if it's got 4 terms, I'll say try factoring it by grouping. All right, and as always at the end of these, I like to say, please read your text. All right, read the material that you're given, whether it be online or a hard copy of a book. Try to work through examples, read through examples, try to understand things as best you can on your own before you go looking for help, because it does make it stick that much more, I feel, when you've accomplished things, learned things on your own. And don't just give up after the first attempt at something. Try multiple times, and if after several attempts and several readings of the text even, well then there's no sign of weakness. It's not weak to go looking for assistance. Look at videos, ask your teacher, tutors, friends, people who have seen it before, and just keep at it. I know with enough time, patience, practice, and persistence, you can accomplish almost anything, especially this. And try to have fun with it as well. And thank you very much. Have a wonderful day.